Hello everyone, this is another Physics 30 example question. This time we're in Unit 5 and Lesson 3. We're still in photoelectric effect. In fact, in Lesson 3 here, we are looking at the really interesting bit of the photoelectric effect whereby Millikan came along and balanced the forces using a voltage. And he then made the assumption that the voltage required to stop these electrons, the energy of that voltage, was the same as the kinetic energy of the electrons themselves. So let's have a look at what's going on. Here's our setup. We have photons coming in. So just as we would normally in a photoelectric situation, we will say that there is a total amount of energy that's initial and a total amount of energy that's final. And indeed, the energy coming in is only from these photons. There's no additional energy, so we can go ahead and put that in. I'll say the energy of the photons. There we go. And that's going to be equal to, well, it's going to be equal to the work function because, of course, I have to have enough energy to liberate these electrons from the metal. That's the concept of the photoelectric effect. But they have more than enough energy to do that. And in fact, they have so much energy that they're able to travel at a certain speed with a certain energy, a certain kinetic energy. So I have to add that on, this EK. Okay, but, well, I'll say that that's the max, the theoretical max speed. However, what Millikan did was he took this this voltage system on the side of our in series with our photoelectric apparatus, and he applied a voltage. In other words, a uniform electric field was applied to this equipment, and he would have made it so that the negatives would have been on this plate and the positives on this plate. And that's because what he was trying to do is create a force, the force electric, which would act on these electrons, which would stop them from having a velocity. He would stop them. So in other words, the velocity of the electron would equal 0. And that means he's made the assumption here that the energy, the electrical energy, is going to be equal to the kinetic energy. Okay, so in other words, the VQ is equal to the 1/2 mv squared. And that's kind of the basis of what we were looking at here. So let's keep that in mind as we move forward, because of course we have an EK max in our energy equation, and we might be able to just switch that out. What do we know? We know that the photons coming in have a certain energy, and we know that there's a stopping voltage of 0.707 volts. So let's start rearranging this. So I'm going to try and rearrange this and solve for the EK max. So I'm going to go, oops, wrong color. I'm going to go energy of the photon. Actually, I should have just kept this to 1. That was bad. This should just be a single photon. Energy of the photon. There we go. So the energy of the photon minus the EK max, that's the maximum energy that these electrons will have, is equal to the work function. And so we have a pretty straightforward formula. Now, one of the confusing things a lot of people get hung up on in these conservation of energy equations is which Planck's constant to use. Now, so what I'm going to do is just follow this through, and we're going to keep in mind the conversion units for our two different Planck's constants. And I'm going to show you a little trick, or at least I want you to be very cognizant of which Planck's constant you're using. So let's just expand this out a little bit, nothing unusual. So we're going to say the energy of the incident photon, let's just leave it as energy for now because we are given the energy here. So energy of the photon, I'm just going to leave that as E, minus the EK max. Well, the EK max, that's going to be kinetic energy, right? So just like that. and that's going to be then equal to the work function, which is going to be hf0. Okay, well, hopefully you can recall when we're talking about EK, so let's just think about this here. We're talking about EK. EK is going to give us a speed. Okay, so let's just think about this. It's 1/2 mv squared. And since we're using v is meters per second. Okay, so meters per second tells us that we need to be, and hopefully you've memorized this, we need to be in joules. In other words, we need to be using the joule seconds version of the Planck's constant if we're going to be extracting this velocity. So we may or may not need to do that, but I'm just going to encourage us to go with it for now. So let's actually start putting in the units. Okay, so let's say we've got the energy, I'm going to use red here, I've got the energy of the photon, which if I keep track of the units, I'm going to keep it in joule seconds. So there's joule seconds, that's my Planck's constant, okay, multiplied by the frequency, which means I'm going to be dividing by s, right? So there's my, notice that the 2 seconds cancel out to give joules, okay? Then I've got EK, which is going to be in joules. Now, what I'm going to do here is just remember that because of the Millikan's experiment, I can say that what's equivalent to EK is VQ. So I'm just going to take out my EK and put in VQ. Okay, still in joules because it's an electrical energy, is equal to my HF naught. And that's going to be, I'm going to keep it in joule seconds just to be consistent. So H is going to be my joule seconds, and then multiplied by the frequency, which is divided by seconds. Okay, so let's think about now how we convert between one Planck's constant and the other. Bearing in mind that we're in joule seconds, so we're using this constant. How do we change from joule seconds to EV seconds? Well, if we use our unit cancellation, we are essentially dividing by 1.6 times 10 to the negative 19. And what's really interesting is that 1.6 times 10 to the negative 19, that is an elementary charge. In other words, that is the charge of an electron. So what you can do at this point is divide everything in your equation, because of course maths tells us that we can do whatever we want to an equation as long as we do the same to both sides. I'm going to divide everything by the charge of an electron. Okay, what does that do? Well, that means that I can now talk about this energy in EV seconds, because remember, dividing by 1.6 times 10 to the negative 19, that gets me to EVs, okay, to EV seconds. Notice that there's my cancellation. If I cancel the joule, I'm left with EV seconds. So that's going to give me, let's put this in, that's going to give me the energy in EV seconds over seconds, minus, well, check this out. I've divided by Q, because this would have been the charge of an electron too. So now I've just got V, okay? And then I keep going. Well, same deal here. This is my H is going to be divided out, which is going to give me my EV seconds. So I have the same situation. So I'm going to have H, Planck's constant, F naught, and this is going to be EV seconds over seconds. So now what I can do, I can actually use the value given in the question, which is EVs. I can bring that down. So that's my incident photon energy. So 4.03 EVs. Okay, because of course these seconds cancel out. Minus the voltage. Well, that's what I've got here. So 0.707 volts is equal to, well, HF naught, this is the work function with the threshold frequency, and it's the threshold frequency I'm trying to find. So I'm just going to leave my F naught here, and that's my in hertz, and then I'm going to divide everything on this side by Planck's constant in eV seconds. So that gives me my threshold frequency is, if I plug in all those numbers, 8.02 to 3 significant digits times 10 to the 14 hertz. Okay, so that's a nice little trick. Hopefully that helps, using this conversion, dividing it all out. Hopefully that helps. Of course, we could have just done it by keeping track of each individual piece. I could have made sure that I had this value here in EVs, and then I could have figured out how to get EVs here and so on. But just wanted to show you, keeping track of the units is really, really important.